functions. So let's look at a particular economic concept. Okay, total cost, marginal cost, we've talked, but let's talk about something called average cost. Okay, so the average cost of producing Q items with a total cost of C of Q is the average cost would be C of Q divided by Q. So you take the total cost of your items, divide by the total number of items you have, and you get average cost. That should make sense. Anytime you're finding the average, take the sum of everything you're working with and divide by the total number. And that's really what you're doing here. So let's say, suppose that a manufacturing an item has a fixed cost of $4,000 and a per item or marginal cost of $20 per item. Let's find the average cost per item when 250 items are produced. So we can look at a total cost function as being the fixed cost plus 20 times how many items we're working with, Q being the number of items we're working with there, okay? And in this case, if Q in this case is 250, then 250 at $20 a pop, that would give me 250 times 20 plus the original $4,000 of fixed cost would give us our total cost. And that's why we're using this linear function here, okay? So then we can talk about average cost by taking that function and dividing it by Q. So if you looked at your average cost for 250 items, plug 250 into this function, and you get 4,000 plus 20 times 250, all divided by 250. Simply plug that in your calculator, you end up with $36. So the average cost per item that we're selling here, it costs us on average $36, okay? So that is this concept of average cost. But this average cost function is what we're going to call a rational function. And in this rational function, what it really defines it is that it's a fraction. Fraction with our variables in the numerator and or the denominator, okay? So looking at this, we could graph this function, we could talk about the behavior of this function, and that's largely what we're going to study in this section. So looking at this particular average cost function, if we were to graph it, which we don't know how to do yet, but we will learn how to do, this graph depicts that average cost function in particular. And what you're seeing here is this axis represents the average cost. This axis represents the number of items. And so we think of this as input and output, the average number of items, okay? Or sorry, the number of items is your input, the average cost is your output. You see that as the number of items goes up, the average cost is going down, but not very quickly, okay? At first, it goes down very fast, okay? If you look at this, as we read this from left to right, at first it goes down very fast, okay? And then after a certain point, somewhere right around here, it's like right around 100 or so, okay, items, the amount that the average cost is going down is decreasing, but it's not decreasing very quickly, okay? So the average cost, and it looks almost like it flattens out. Now this does not, in this area here, flatten out. It does continue to go down, but very, very slowly. So understanding how this function works and its behavior is by graphing it, and then reading that graph and understanding that graph, which is a more valuable tool, shows you kind of the behavior as you look at the number of items and where kind of that number of items, in this case, it changes drastically in terms of decreasing very quickly and then decreasing very slowly. So let's define a rational function. A rational function is a function of this form where we have a polynomial n of x divided by a polynomial d of x. So this numerator is a polynomial, this denominator is a polynomial. So in this case, these polynomials, we look at the domain of each one, okay, and then we can use that to find the domain of the whole thing. Largely, since this is a fraction, you don't want the polynomial in the denominator to equal 0. If the polynomial in the denominator equals 0, then this function is undefined. You can't divide by 0. So first thing we want to talk about is domain. The simplest rational function we can come across is this one called the reciprocal function. We've talked about this lessons prior. Okay, it came up when we looked at a bunch of common functions, but now we're going to talk about it in earnest. So thinking about this one, if you look at this here, okay, the denominator is x. You don't want that denominator to be 0, so you don't want x to equal 0. So if we said, what's the domain? Well, we can say the domain is the set of all x such that x doesn't equal 0. Okay? So you can't have that value. Any other value is fine, but you can't have that value. This is different than polynomial functions where the domain was all real numbers. Now, graphically, what that means is that our graph is going to be broken into pieces because there'll be certain x's we can't use. Therefore, the graph will be divided into separate curves. Two things that largely define the behavior of a rational function are the concepts of asymptotes. We have two that we'll discuss right now. There are three total, technically, but we'll talk about these two first. Horizontal asymptote and a vertical asymptote. So let's look at one at a time. So let's look at our horizontal asymptote here. Okay. Horizontal asymptote is going to be some horizontal line that your function will get closer and closer to as x goes to either positive or negative infinity. So if x is getting closer to negative infinity or x is getting closer to positive infinity, you're really talking about the ends of each graph. Okay? This is where x is getting closer to negative infinity. This is where x is getting closer to positive infinity. And as you reach the end of your graph, you're going to get closer and closer to some constant y value. So there's going to be some horizontal line, and your graph is going to get close to it as you get to one of the ends or both of the ends. Okay? That's very different than polynomials. In polynomial functions, as we went further and further down to the left to the right, as x went to positive or negative infinity, the y values were increasing all the way up to positive or negative infinity. But now we're talking about the y value getting closer to a horizontal line. That would be our horizontal asymptote. Vertical asymptote is sort of the same thing in opposite nature. The y value is going to go to positive or negative infinity as x goes to a constant. So what happens here is we have a vertical line, and x is getting closer and closer to this constant value, this vertical value, okay, vertical line. And then the graph of the function, or the y values, will either shoot up to positive infinity or shoot down to negative infinity on either side. Sometimes both sides go to positive infinity, sometimes both sides go to negative infinity. Sometimes one goes up, one goes down. You know, which one of these options you have changes for function, but the idea is x is getting closer to a constant now, which means x is getting closer to some value here, so place a vertical line here, and then as the y value, you know, is evaluated, the y value will either go to positive or negative infinity. And that's what defines a vertical asymptote. And these really affect the behavior of the function. Better understanding of asymptotes by looking at a couple of visuals for these functions. So let's look at this first one. In this case, here we're dealing with this function, okay, 2x plus 1 over x plus 1. This function has two asymptotes. It has a vertical asymptote at x equals negative 1. So here's an x value of negative 1. There's this vertical line through negative 1. That is my vertical asymptote. There's a horizontal asymptote. The horizontal asymptote is at y equals 2. There's this horizontal line that goes through a y value of 2. So let's study each one individually. Let's start with the vertical asymptote. So in this vertical asymptote here, okay, x is going to creep ever so close to that value from the right-hand side and the left-hand side. So let's focus on the right-hand side. As I use each one of these x values here, I'm going to get a point on the graph for each one of those x values. And if I follow the y values that I'm getting, those y values are continued to go further and further down to negative infinity. And if I keep getting closer and closer to this x value, the y value is going to continue to go down further and further and further to negative infinity. So x is getting closer to this constant number, but the y is stretching down to negative infinity. The opposite's happening on the other side. As x value gets closer this way to -1, okay, and I look at the corresponding points that I would get as I keep getting closer and closer to -1, okay, the y value is actually stretching up to positive infinity. So what happens is my x is getting close to this constant number from one side or from the other side, but the y values are shooting down to negative or positive infinity as I get closer to this vertical line, to this x value. That is the definition of a vertical asymptote. Now let's erase some of this. Let's talk about horizontal asymptote. Horizontal asymptote is the same idea, except horizontally. So the idea here is we have this horizontal line at 2. And the horizontal asymptote discusses what happens when x goes to infinity or x goes to negative infinity. So the ends of the graph, here and here. If I let x not go to a constant number like -1, but x is going to an infinite value, positive or negative infinity, what's happening to the y's? We saw in a polynomial function that the y value could increase, to infinity as x goes to infinity, or decrease to infinity as x goes to infinity. But that's not what we're talking about here. We're talking about the y value getting closer and closer to some number, some constant, in this case 2. So as I look at all the x values as I go, my graph goes this way. My y values are not going to keep getting bigger and bigger and bigger and going to infinity, but instead they're going to keep getting closer and closer to this horizontal line, which has a y value of 2. Now this graph is never going to touch that horizontal line. It's always going to just creep closer and closer to it. It'll never get to it. It'll never cross it. And that is what's happening in a horizontal asymptote. Same thing on the opposite end. As x goes to negative infinity, the y value is going to get closer and closer and closer to this horizontal line, and that's why we call that a horizontal asymptote. One thing that's a common misconception is that you can't cross a horizontal asymptote. You can cross a horizontal asymptote in the middle. You cannot hit it at the ends. The idea is you approach that horizontal asymptote on either end. Here's another one. In this case, this function here has a horizontal asymptote at y equals 0. It does not have any vertical asymptotes. That's a possibility. But if you look at the end of the graph, y equals 0 is the x-axis. At the end of the graph, this function gets closer and closer and closer to the x-axis on this side and the x-axis on this side, which is a y value of 0. So as x goes to infinity, y is getting closer and closer to 0. Function that has this shape to it is a bell shape. Sometimes we call this the bell function or the bump function. Lots of different functions can have that shape. This is just one of them. But in this case, here's an example that has a horizontal asymptote but no vertical asymptote. And here's one that has both a vertical and a horizontal. Here, this vertical asymptote is right here at 1. The difference between this one and the first one is on either side, as I get closer to it from this side or from this side, this value of 1, the x values will send my y values up to positive infinity on both sides, okay? So if I get close to 1 this way, I go up to positive infinity. If I get close to 1 this way, I go up to positive infinity. That can happen. One side can go up, one side can go down, both can go up. We'll figure this out as we calculate these asymptotes. And just delete all this, you see on the ends we have a horizontal asymptote of 0 again, here and here. I get close to the y-axis on this end, the x-axis, I get close to the x-axis on this side, okay? So my horizontal asymptote is y equals 0. All right, so now how are we going to find these asymptotes? So it's actually really simple. Let's start with vertical asymptote. So we're looking at a rational function. In this rational function, the numerator is a polynomial function, the denominator is a polynomial function, and we're going to say that both of them have no common factors. What that means is that this fraction is simplified as much as possible, because that will make a difference. If they do have common factors, we'll talk about that in a second. But if they don't have common factors, the vertical asymptote is going to be where the denominator, d of x, is 0. So let's look at a couple of examples, then we'll talk about what if it's not simplified. So here's a function. You can't factor either the numerator or the denominator, therefore it is simplified as much as possible. You look at the denominator and say, well, when would this denominator, 3x squared plus 1, equal 0? Well, it'll be when 3x squared equals negative 1, or x squared equals negative 1/3. In the real number system, okay, a square can't equal a negative, so this has no real solutions. So that means this denominator is never equal to 0. So then there is no vertical asymptote in that scenario. Look at the next one. You can factor the denominator, but it doesn't help you simplify. X minus 1, x plus 1 simplifies that denominator. 2x squared in the numerator, nothing cancels. So it's simplified as much as possible. So if I set that denominator equal to 0, I get x equals plus and minus 1 as my solutions. Well, those are my vertical asymptotes. Okay, I have two of them. One at positive 1, x equals positive 1, that vertical line. One at x equals negative 1, that vertical line. Okay, look at the next one. Also simplified as much as possible. I can't factor either one. The denominator is x. When will x equal 0? Well, when x equals 0, that's my vertical asymptote. So finding the vertical asymptote is very simple. Now, what if this is not simplified? What if there are common factors here and here? What are we going to do? Well, look at this. If n and d, the numerator and denominator, have common factors, then f of x will only have a vertical asymptote at the x values that are zeros of the denominator but not the numerator. If they share a common factor, they share a 0. And so you're only going to look at the zeros that are zeros in the denominator but not the numerator. So what we're going to say is that if we look at the common zeros between the numerator and denominator, the common zeros actually result in a different kind of discontinuity, which we call a removable discontinuity, or essentially a hole in the graph. And I'll show you some examples of that. Before we get into examples of those removable discontinuities or holes, let's just talk about horizontal asymptotes. So we know how to find a vertical asymptote. Make sure your fraction's simplified as much as possible. Make sure the numerator and denominator don't have any common factors, and let the denominator equal 0. If they do have common factors, then only focus on the zeros of the denominator that are not zeros of the numerator. Common zeros between the numerator and denominator result in those holes. All right, so let's look at horizontal asymptote. Polynomial over polynomial, no common factors between the numerator and denominator, so let's make sure we're simplified. If they do have common factors, then cancel them out. Okay, simplify this fraction as much as possible. Then we're going to find a horizontal asymptote based off of the degree of these two polynomials. What is the degree? The degree is the highest power each variable is raised to in the numerator and denominator. So x would be our variable, most likely, so the highest power of the variable from the numerator and denominator. Your options are you're either going to have one horizontal asymptote or no horizontal asymptote. You're not going to have multiple horizontal asymptotes. Like we saw in the previous, one of those examples had two vertical asymptotes. That doesn't happen with horizontal. So if the degree of the numerator and denominator are compared, then we could determine what we have. So n is the degree of the numerator, and m is the degree of the denominator. If n is less than m, numerator's less than denominator's degree, y equals 0 is your default horizontal asymptote. If the degrees are the same, We divide what's called the leading coefficients. So whatever number is in front of that highest power variable, those get divided, and y equals that value is your horizontal asymptote. And if the degree of the numerator is bigger than the denominator, there is no horizontal asymptote. So I give you those three examples right here. So all three examples, same ones we just dealt with a second ago. Each one is simplified as much as possible. Now let's look at it. The degree of the numerator, there's a 1 here. Degree of the denominator here, there's a 2. So in this case, the numerator is smaller than the denominator's degree, because 1 is less than 2. In that case, y equals 0 is your default horizontal asymptote, HA. Here, the degrees are the same. N is 2, M is 2, N equals M. So what we're going to do is we're going to focus on the coefficients in front of that highest power term. There's a 2 here, there's a 1 in front of this x squared. So if I let y equal 2 over 1, this one divided by this one, that will be my horizontal asymptote. So y equals 2 is what that simplifies out to. And finally, this one, the degree here is 2. The degree down here, there's a 1. The numerator is bigger than the denominator's degree. 2 is bigger than 1. Therefore, there is no horizontal asymptote in that scenario. So if we're going to try to analyze the graph of a rational function, we want to sort of build that graph up based off of some very common features of that function. So here would be the steps we should follow. So first off, we want to make sure that our polynomial is in the numerator and denominator are simplified as much as possible so that the numerator and the denominator have no common factors. We will get to the situation and I will show you the example where they do have common factors. I know I haven't done it yet, we've talked about it, but let's start off by saying we're going to simplify this fraction as much as we can so that the numerator and denominator have no common factors. Assuming that that's the scenario we're working with, first thing we're going to do is we're going to find the zeros of the denominator. The zeros of the denominator, so where the denominator equals 0, essentially will give us the vertical asymptotes, and we will sketch those out. Next step, we're going to find the horizontal asymptotes and sketch them out based off of the rules we talked about for finding the horizontal asymptotes based off of the degree of the numerator and the degree of the denominator. Next, we will find and plot the y-intercepts. How? Same way we've always found and plot the y-intercept. Let the x value equal 0, so essentially find f of 0. Next, we're going to find x-intercepts. We're going to find x-intercepts by letting the function equal 0. Well, if you're letting the, well, let's take a step back. We're going to let the function equal 0. If that function is a fraction, numerator and denominator, the only time this fraction could equal 0 is if the numerator equaled 0. So, simply find zeros of the numerator, this, and that will give us the x-intercepts. Finally, there will be some holes, or some I don't want to use the word holes. Let's take a step back. There will be some missing parts that need to still be filled in because this steps 1 through 4 won't necessarily give us everything. So we're going to want to plot some checkpoints to kind of fill in some of the missing pieces. And normally your rule is at least 1 point between and beyond each x-intercept and vertical asymptote, but we'll talk about that as we go. And then finally, kind of connect this all together with smooth curves to complete your graph. Okay? So these will be the 6 steps we'll follow in order to analyze the graph of a rational function. With something very simple. So in this case, working with this function, first off, it is simplified as much as it can. There are no factors of the numerator and denominator that we can have that will cancel each other. So, first step, find the vertical asymptote. In this case, the denominator equals 0, gives you x equals 2. There's your vertical asymptote. 2, we want to find the horizontal asymptote. Well, the degree of the numerator, you would say, is 0. There is no x up there. It's just a 3. So the power on the x, you could say x to the 0 is 0. Denominator, 1. Denominator is bigger, so y equals 0 gives us a horizontal asymptote. Next, we want to do our y-intercept. So we'll find f of 0. In this case, 3 over 0 minus 2 gives us negative 3/2. 4. We are going to find our x-intercepts. So we let the function equal 0, but that function is 3 over x minus 2. Since it's a fraction, the only thing that has to be 0 is the numerator. Well, 3 never equals 0, so that tells me there are no x-intercepts. Okay. What we want to do is, step 5, is plot checkpoints. Well, that's going to be based off of all this information that we just came up with. So let's start putting all this information in an XY plane and see where we can best get use of these checkpoints. Okay, we have a vertical asymptote at x equals 2. So here's 1, here's 2, here's our vertical asymptote. Okay, we would typically like to use a dotted line or a different color line. You're probably going to use the same color, so dotted line's probably better, so we don't confuse this with anything that's actually on the graph of the function. We have a horizontal asymptote, so that was again x equals 2. We had a horizontal asymptote at y equals 0 being the, let's get a color you can see, being the x-axis. So here you can see that's my horizontal asymptote, that's y equals 0. We saw that we had a y-intercept at negative 3/2. So here's negative 1, here's negative 2, negative 3/2 is in between. So we have that y-intercept, and there are no x-intercepts. So the graph is never going to cross the x-axis, ever. So we need to start graphing our function. I will use the color, what have we not used yet? Green, to show the actual graph of the function. I will say that I know for sure this needs to happen. Why do I know that? Well, I know as I get close to my vertical asymptote, my graph has to either go up or down. So I know I go through this point right here. Guaranteed, that's a y-intercept. I found it. So as I travel towards this x-intercept here, I either go up or I'll go down. Well, up is not an option. It's not an option because I would have to cross the x-axis. I know my function doesn't cross the x-axis, so I can get rid of all this, and I know that I have to go down. So this has to happen here, just because I know I go through this point. As I travel the other way, I know I have to get closer and closer to this horizontal asymptote right here, and I know I'll never cross that horizontal asymptote because, not because it's a horizontal asymptote, but because I don't have any x-intercepts. So my graph has to get closer to that horizontal asymptote, and therefore that has to happen. If you're not sure, take one of these x's, negative 1 or negative 2. Plug it into our function. Remember, our function was 3 over x minus 2. See what kind of y value you get. You're going to get a y value that's going to creep closer and closer and closer to y value 0, but be negative, be below 0. Now over here, I have no idea what happens. Okay? No idea. So that's where I'm going to need a checkpoint. So we have x values, 3, 4, 5, pick any one of them. So let's pick, say, 4. I'll plug that into my function. I'm going to find f of 4. That'll be 3 over 4 minus 2, which will give me 3 over 2. So this x value has a y value of 3 halves. So here's a y value of 3 halves. So that gives me a point right about there. Now, for all the same reasons I just said before, I know my graph has to do this. Okay? And this is kind of sloppy, but that's what my graph has to do. Now, why? Because if my graph has to go through this point, then as I get closer and closer to this vertical asymptote, my graph's either going to shoot up or down to positive or negative infinity. But down isn't an option because I would have to cross the x-axis. I know I don't, so let's get rid of that. Up is the only way to go. And as I move towards positive infinity on the x-axis, I have to get closer and closer to this horizontal asymptote. Well, I'll get close to the horizontal asymptote. I know I can't cross it because it doesn't have any x-intercepts. The fact that I have no x-intercepts, people might think tells me nothing. It actually tells me quite a bit. Knowing I'll never cross the x-axis really tells me that I'm stuck with certain behavior of my function. So this is my graph. That's a kind of sloppy looking version of the graph. This would be a much cleaner looking version of the graph. You see we have a vertical asymptote at 2. We have a horizontal asymptote at 0. We go through this point, negative 3 halves, and then we have other values in between. So this would also be positive 3 halves. That's a much cleaner shape. This here and this here, but that's because it's drawn by a computer. Obviously, drawn by hand will be a little bit sloppier. Another one. So here's g of x. Notice this function is simplified as much as possible. You can't factor each numerator anymore, and there's no common factors. So let's start. 1, vertical asymptote. Denominator equals 0. Super easy. X equals 0. 2, horizontal asymptote. Look at the degrees. The degree of the numerator, there's a 1. Degree of the denominator, there's a 1. So what do? We look at the leading coefficients. That's a 2, that's a 1. So y equals 2 over 1, or 2 is your horizontal asymptote. 3, y-intercept. Find f, or in this case g, of 0. Well, that'll be 2 times 0 minus 1 over 0. Notice, you're dividing by 0. You can't do that. So there is no y-intercept. 4, x-intercept. Well, we let the function equal 0. Again, because it's a rational function, we really only have to let the numerator equal 0. Well, if you solve that, you get x equals a half. So there's your 1 x-intercept. So we will put this all together so that we can do our checkpoints, and we will get the graph of our function. So vertical asymptote, x equals 0. So that will be the y-axis. Horizontal asymptote, y equals 2. There is no y-intercept. That's because the vertical asymptote is the y-axis. So if the vertical asymptote is this y-axis, you can't cross it. So there's no y-intercept. So these two things basically go hand in hand. X-intercept, 1/2. So here's 1, here will be 1/2. Okay? And we'll go draw our graph. So I'll use this orangey yellow color, and I would say this has to happen. For all the same reasons. I know I go through this point. I know I have to get closer to this vertical asymptote at x equals 0. And so my graph has to go down this way. Also, I have to approach my horizontal asymptote on the end, so my graph is kind of stuck in this shape. Now on this other side, I don't know. I have no idea what will happen here or here. So what I'm going to do, erase that, is plot a checkpoint. So I'll use, I don't know what's on this side, -1, maybe -2, maybe -3, any one of these. All three of them, one of them. You need something. So let's start with something easy. Let's go with -1. So if I find g of -1, that would be 2 times -1 minus 1 over -1. And what does that give me? It gives me -2 minus 1 over -1, which gives me -3 over -1, or 3. So this 1x, -1, gives me a y value of 3, which gives me a point right here. That alone tells me that my graph has to be up here, and therefore my graph has to do this. Again, I have to approach my vertical asymptote here, I have to approach my horizontal asymptote here, and I know I go through this point, so that would be where my graph has to be. Clean it up a little bit, make it. Here's a much neater graph of what we just looked at. See, we go through this x-axis, we have the horizontal asymptote at 2, vertical asymptote at 0, going through this x value of 1/2, having these different points, -1/2, 3, we'll be right about there. So we have this shape, we have this shape. Here's yet another one. Okay, each one I give you is a little bit more complicated than the last, but these are all things you would see along the way. So we want to try and make sure this is simplified. It is. Now this denominator can be factored, but there are no common factors between the numerator and denominator. If you factor the denominator, you see you're going to get x, -2 times x plus 1. But there's no factors that are shared, so it is simplified. So if we go through our steps, first step, vertical asymptote, denominator, x minus 2 times x plus 1, I'll use the factored form because it's easier. When does that equal 0? Well, when x equals 2 and when x equals -2. Or sorry, -1. All right? 2, find your horizontal asymptotes. The degree of the numerator is 1, the degree of the denominator is 2, so y equals 0 is our default horizontal asymptote. 3, y-intercept, we let x equals 0, so in this case we have h of 0. That would give me 0 over 0 squared minus 0 minus 2, so that gives me 0 over -2, which is 0. And 4, we got our x-intercept. Again, we let the function equal 0, but that amounts to just letting the numerator, which is x, equal 0, and so there's your x-intercept. So we have our y-intercept, we have our x-intercept, we have our horizontal asymptote, and we have 2 vertical asymptotes. That is different from the previous 2 examples. So what we want to do is we want to put all this together. Let's put it all together. We have 2 vertical asymptotes. One at 2, one at -1. We have a horizontal asymptote at 0, so that's the x-axis. And we have an x and y-intercept both at 0, which puts us at the origin. You do cross the horizontal asymptote in that this is on the horizontal asymptote right here, but that's fine. Remember, the horizontal asymptote only describes what happens at the ends of the graph. In the middle of the graph, anything can happen as it relates to the horizontal asymptote, so that's okay. Now, I will tell you that your graph either has to do this or this as you leave this point. Not both. If you did both, you wouldn't pass the vertical asymptote, but you do one or the other. In order to figure out which one it's behaving like, I'll take a checkpoint in here. Let's call it 1. And I would have to find f of 1 for this function. Well, if you plug 1 into the function, I'm not going to bore you with that, plug 1 into the function, you end up getting -1/2. So the y value for this x value is down here, thus giving me this curve, and therefore this one can't happen.
Same thing, as I leave this point going the opposite way, I'm either going to do this or this. The only way I know is to take a checkpoint in here. Negative 1/2 would be an x value in here. Unfortunately, it's fractional, but you still should do it. Find f of negative 1/2, see what you get. Well, if you see what you get, you're actually going to get 2/5, which is up here. It's positive. The fact that it's positive and it's up here, 2/5, 3/5, 4/5, the actual value just tells me the location, but really what's important is it's positive. That means this lower one can't happen. So right now, the middle of my graph has this kind of S-curve shape to it in here. Okay. Now I got to figure out what happens on this side of 2 and on this side of negative 1. Well, plug another checkpoint in. 3 is over here, 4, 5, pick any one of them, doesn't really matter. I'll do 3. So if I found f of 3, what do I get? Well, in this case, I'm going to get 3/4. So I have 3/4 as a point. It's there. That alone tells me my graph has to be up here. I have to approach my vertical asymptote and my horizontal asymptote. I can't cut down this way because it would cross the x-axis. I know I don't cross the x-axis down there. So that's my graph. Same thing over here. Take one of these x values over here. So we got negative 2, negative 3, negative 4. Any one of them will work. So if I found f of negative, say, 2, I end up getting negative 1/2 as my y value. Again, just plug it into the function. Well, if I get negative 1/2, this x gives me a y value down here, thus telling me that my graph has to be down here and shaped within inside those asymptotes. So I have 3 different portions to my graph. This portion here, this one inside, and this one over here. If you want to look at a neater version of this, I mean, that's not too bad, but looking at this next one, that's what my graph would look like. You see I go through the point 0, 0. I have a vertical asymptote at 2, another one at negative 1 would be right in here, okay, and my horizontal asymptote at 0. And so you see your graph fitting inside those vertical and horizontal asymptotes and curved within them. But the difference of this function versus the last couple is there's now 3 pieces. That's because we had 2 vertical asymptotes, breaking it into more pieces. All right, now with all 3 of those examples, I largely danced around the idea of having a common factor in the numerator denominator. Every one of those examples was already simplified from the start. So what I want to do is look at one that's not, so that you know how to deal with it. There is not much of a difference. It's just the starting point is different than the starting point of those other ones. But the steps largely are the same. You're going to find the vertical, you're going to find the horizontal, you're going to find the y-intercept, you're going to find the x-intercept, you're going to put it together. But the first step is different in that the first step is you're going to have to simplify it and realize what factors you canceled out in order to simplify it. So if we look at this function here, I can simplify this function. The numerator is x minus 2. Fine. But the denominator is x minus 2 times x plus 2. So I can cancel this x minus 2 and this x minus 2, leaving me with 1 over x plus 2. This is the simplified version. What I would do is now follow all the steps that we just talked about with this version of my function. So vertical asymptote, horizontal asymptote, y-intercept, x-intercept, and do it exactly the same because it's simplified. There are no common factors. But I need to realize that that's not where I started. I started here and I canceled this factor out. Well, that factor I canceled out, x minus 2, I need to look at when would that be 0. Well, it would be 0 when x equals 2. So that is a value I want to omit from the domain of this function. I don't want it to be in my domain. Y will make my denominator 0. What happens though, but since I was able to cancel that factor out, and now I look at this, if you notice, that particular value, okay, when I plug into this new one, doesn't make this denominator 0. So what happens here is this will relate to a break in the graph, but not a break in the graph that's a vertical asymptote. Instead, it'll be a break in the graph that is what we call a removable discontinuity, or simply a hole. Now that's the x value for the location of the hole. To find the y value, I will plug it into here because I can, because it doesn't make that denominator 0, and I'm going to see I'm going to get 1 over 2 plus 2, which equals a fourth. So essentially the point 2 comma 1/4 will be a hole in the graph of this function, and then everything else about this function can be found using our normal steps. That's the additional component that we didn't have to deal with in the previous examples because they didn't have any common factors to start with. But if you do have a common factor, that's what you do. So you're going to cancel out the common factors, graph the following procedure that was described earlier, right? Do everything else with the simplified rational function. Then you're going to set the factor that you canceled out, or factors you canceled out, from the original rational function equal to 0. What x values you get out of that will be the holes in the graph. So, if we were to graph this function right here, we would simplify it and get this. We would find our vertical asymptote. Okay, let me get some space here. We would find our vertical asymptote. Let's use blue. Actually, let's use red. Which would be x equals -2, because that's when the denominator equals 0. The horizontal asymptote would be y equals 0, because the denominator has a bigger degree. There would be a y-intercept at the point 0, 1/2, because if you let x equal 0, you would get 1 over 2. There would be no x-intercept, because the numerator will never equal 0. And there will be a hole at this point right here. So this is all the information we know. Let's put it all together. So what did we say again? We got it. Vertical asymptote at -2. Okay. We got a horizontal asymptote at 0. That's the x-axis. It's a very common one. We got 0, 1/2 as my y-intercept. So if here's 1, here's the y-intercept. Okay. There is no x-intercept. And we have a hole at 2, 1/4. So there. To represent that as a hole, what I should do is use an open circle. So I'll make it really dramatic, a big open circle. So I know my graph goes through this point, doesn't hit the x-axis, so I know my graph has to curve this way. And as it comes this way, it's going to delete that one point, and it's going to keep going. Okay. Again, I made this hole a little dramatic, but basically it's one point missing in the graph. I have to approach my horizontal asymptote. I have to approach my vertical asymptote. It can't turn down because it would have to hit the x-axis. It doesn't hit the x-axis. All right, I need a checkpoint over here. Let's go -3. So if I plug -3 into the simplified version, which was 1 over x plus 2, I would simply get f of -3 to be 1 over -3 plus 2, so 1 over -1. So it would be down here, thus making my graph look like this. No holes over here, all one solid piece. And that would be the way you graph it. Notice there's really not much difference. If I was graphing just this function, f of x equals 1 over x plus 2, if that's what I was starting with, then it would look exactly the same as this, except it wouldn't have this hole right here. It would just be all one solid piece the whole way. But because I started with this function, which is x minus 2 over x minus 2 times x plus 2, then my graph basically looks exactly the same, except for because I was able to simplify this into this, I have to worry about that thing I simplified or canceled out, thus giving me that one difference, the hole right there. This whole thing up with an application. So, Natty Products, an eBay retailer that resells items purchased from Fiji, has started selling a new-to-market product. Natty is currently selling 2,000 units a month of this product, which has been growing by 100 units a month. The total market for the product is currently 10,000 units, but is growing by 100 units a month. There's a lot there, so let's unpack it. First, we'll determine Natty's current market share. Then, we'll find the horizontal asymptote and interpret it in context of what this scenario is all about. So, let's look at this. So the sales per month are increasing linearly. Okay? So let T be the number of months, then Natty sales per month are going to be 2,000 plus 100T. Why? Because she's currently selling 2,000 units a month and growing at 100 units per month. So you start at 2,000 and you're growing by 100 per month, T representing the number of months. Okay? So that's that. And the total market share is 10,000 growing at 1,000 units per month. Okay? So that's the market share. So this is Natty's, this is the market share based off of what it currently is and how much it's growing. I think that's pretty easy to follow. So then what we want to do is we want to look at Natty's market share, okay, as a fraction of the total market. So you just take Natty's divided by the total, and that will be basically the market share, Natty's versus the total market. So if we look at Natty's current market share, not future but current, the number of months we're working with is 0. So she's at 2,000. The current market is at 10,000. So she's at 2,000 over 10,000, or put 0 into this function, and you get 0.2, or 20%. She's virtually working at 20% of the market right now, which is pretty easily understood. If she's at 2,000, the market's at, 10,000. All right. But let's make sense of this in terms of what we learned. Find the horizontal asymptote for this function, and let's interpret what that really means. The horizontal asymptote is easy to find. We have the same degree in the numerator as we do in the denominator. And when the degrees are the same, we look at the leading coefficients in front of those. So in this case, we would take 100 divided by 1,000. So our horizontal asymptote would be 100 divided by 1,000, or 0.1. So if we were to graph this function, but really just look at the function versus the horizontal asymptote, we would have a horizontal asymptote here at 0.1. And if we look at the behavior of this function, this market share function, in relationship to the horizontal asymptote, it should approach it. Okay? So what does that mean in terms of this particular problem? What it means is that if we keep putting in a large input, so if we let the number of months increase more and more and more and more, and we look at Natty's market share versus the total, okay, what's going to happen is that her market share will get closer and closer and closer to 10%. She's currently at 20%, right? She's currently here. That's at 0. But as time moves forward, as the number of months moves forward, she will get closer and closer and closer to a market share of only 10%. Her market share will be going down and it will be approaching 10%. She won't go below 10%. She'll never get below that. That's where she's going to get closer to as time goes on. So she's got to realize that her market share will decrease and her market share will approach that 10%. Obviously, you would want it to go up instead of go down. But still, if you're approaching a horizontal asymptote, it's going to not go up infinitely. It's going to go up and flatten out to a certain amount.